motivate them like this. So kind of our progression we've been going through is introducing larger and larger families of functions. Right, so we introduced linear functions. We studied those for a little bit. We introduced degree 2 polynomials, quadratic functions. You can do anything you want to with them. We started introducing high order polynomials, talked about why you need to study them to do some modeling. Talked about a few things you can do to study them explicitly. Their graphs are also reasonably well understood, so you can answer questions just graphically about them. Today I'll introduce another family of functions called rational functions. And in order to motivate what they are, let's just look at those top 5 functions. Tell me, are these polynomials? Are these polynomials? Is 5 a polynomial? Folks for yes? Folks for no? It is a polynomial. We technically have to regard constant functions as polynomials. Constant functions are degree 0 polynomials. And let's do this one next. 4x to the 5th plus 4x minus 2, is that a polynomial? Yeah, it is literally, it's a sum of a bunch of coefficients next to powers of x. It's a polynomial. Maybe I'll even indicate that this is a degree 5 polynomial. What about 1 divided by x? Is that a polynomial? No, you're not allowed to divide by x in polynomials. This thing is not a polynomial. What about x plus 1 divided by x minus 1? Is that a polynomial? No. Again, you're not allowed to divide by the independent variable in polynomials. You're only allowed to divide by constants. And maybe that last one just to remember. X plus 3 times x plus 2 times x minus 1. Is that a polynomial? Yeah. You could FOIL it out. And then you would see that it's a polynomial. What degree is that polynomial? But these two things that were not polynomials, they're built out of polynomials, though, right? They're just built out of polynomials with division. So chances are, I could study a function that looks like x plus 1 divided by x minus 1 by just knowing things about x plus 1 and things about x minus 1. So chances are that's still a type of function that I could study. That's what we'll introduce today. We'll introduce functions like that. I'll call them rational functions. A rational function is anything that is a ratio of polynomials. Just like a rational number is anything that is a ratio of integers. That is, a rational function is anything in the form p of x divided by q of x, where p and q are polynomials. I guess q had better not be 0. You better not divide by the 0 polynomial. So tell me, are these rational functions? X squared plus x squared minus x divided by x cubed plus 10. So it's a fraction. Is the numerator of that fraction a polynomial? Is the denominator of that fraction a polynomial? So is it a rational function? Yep. One divided by x cubed minus 1. Is that a rational function? And maybe I'll pause for a second, just let you gather some thoughts. Folks for yes it is? Anyone for no it isn't? Oh good, right, because 1 is a polynomial. That's why I need constant functions to be polynomials. Otherwise 1 over x wouldn't be a rational function. X plus x inverse. Is that a rational function? So think about that for a second. And now let's test the waters? Folks for, I think it is a rational function? Folks for, it isn't a rational function? Nice. So let's simplify it a little bit. So that 1 over, that x inverse, that's just 1 over x. So let's think about it this way. This is the same thing as x plus 1 over x. So I see that's like a number plus a fraction. If you want to like add them and simplify, you want to get like a common denominator. What would that common denominator be? X. So let's rewrite that as, I guess that would be x squared divided by x plus 1 over x, also known as x squared plus 1 over x. Cool. So same question again then. Is that a rational function? Folks for yes? Anyone still for no? Yeah, it's a rational function because we could simplify it down to get it into the right form. How about that fourth complicated looking thing? Is that a rational function? I'll let you think about it for a second. So what do you think? Is that rational? Folks for I think it probably is. Folks for it is not. So I think it is, and let's maybe even explain why without doing it. So this already is like a polynomial divided by a polynomial. Could you rewrite this piece as being a polynomial divided by a polynomial? Yeah, you would just like put all of that stuff in the numerator, right? That's how you multiply fractions. So you now have a fraction minus a fraction. You could get a common denominator. What would that common denominator be? Yeah, just the product of the two denominators. So you could rewrite both of those to have common denominators. Then you could add fractions. Oh, hey, does it suddenly have the form polynomial divided by polynomial? Sure does. So that is also a rational function. In fact, anything that is a sum product difference of rational functions is a rational function. What about x cubed plus x plus 1? Is that a rational function? Let people think for a second. All right, what do you think? It is a rational function? It is not a rational function. Nice. So, what if I do this? Is the numerator a polynomial? Is the denominator a polynomial? That's why I need constant functions to be polynomials, because I want every polynomial to still be a rational function. You should still study it as a polynomial. You should study something by putting it in the simplest class it lives in. Every polynomial is rational. And now the square root function, the square root of x. Is that a rational function? All right, people seem to be coming to conclusions. Let's see what intuition says. The square root of x, rational functions? Not a rational function. All right, reasonably well split. I'll come back to the square root function as soon as I make it to the bottom of the page and I reveal some properties of the square root function, of rational functions. And right, the property will be something graphical. So tell me, what does the square root function look like? It has domain that looks something like this. What's the domain of the square root function? Zero to infinity. So I'll think about those two facts. I'll think about graphs of a rational function and domains of rational functions. I'll see if any rational function could have that as its graph. If not, then it's not a rational function. So here's, before I do that though, right, whenever you're talking about like rational numbers, rational functions, anything that's a ratio, step one should be eliminate common factors if possible. So Just like you would say 2 over 4 is just 1/2, so I'll study a half. I won't study 2/4. If you saw x squared plus 1 divided by x minus 2, times x minus 2 divided by x minus 2 times x plus 1, you would cancel those factors and say, well, that's the same thing as x squared plus 1 divided by x plus 1. Unless you had a good reason to put those added factors there, like say you needed a common denominator to add stuff. So let's think about graphs of rational functions, with the payoff being a fact about this. So there's a graph of 1 over x. There it is. Does that look like it could possibly be the graph of a polynomial? Why not? Well, let's see. Are there any breaks in the graph? If I wanted to sketch that graph, could I do it without picking my pen up? No, because there's this really big jump from minus infinity to plus infinity. On the other hand, if you sketch the picture of a polynomial, right, a polynomial will have some number of floating points, but it won't have any breaks in it. This does have a break in its graph. It has a jump at x equals 0. Polynomials don't. Polynomials don't have any breaks in their graph. They don't jump. Let's think about domains. What's the domain of that function? Yeah.
Negative infinity to 0.
Because you can't divide by 0. So the same sort of thing is true about rational functions. If I give you a rational function p over q, which are in reduced terms, meaning p and q have no common factors, then the graph of that rational function will have no jumps except when the denominator is 0. And when the denominator is 0, you'll see y values that shoot off to plus or minus infinity. Gesundheit. So, just like there's the graph of 1 over x, the denominator is just x. That's 0 when x is 0. So there should be a jump when x equals 0 from minus infinity to plus infinity. Yeah. Oh, yeah. There. I think that's as far as I dare. Is that better? Maybe I'll even hit the focus button in hopes of that making it better. So let's also say one other thing about domains. So if I want to study something that looks like p of x over q of x, well, p and q are both polynomials, right? What's the domain of a polynomial? Everything from minus infinity to infinity you can plug into a polynomial. So you can plug anything into p, you can plug anything into q. But there's some division going on. What's something I can't divide by?
0.
0, good. That's the only bad thing that can happen. So this has domain equal to everything but zeros of q of x. So let's suppose that q was like a degree 20 polynomial, pretty high. How many zeros can a degree 20 polynomial have? 20, finitely many. In general, if you have a rational function, how many zeros can the denominator of that rational function possibly have? Well, it'll be at most the degree of that polynomial. So it'll always be finite. It could be like a billion, but it'll be finite. Only finitely many numbers missing from domain. Let's go back to the square root function. How many numbers are missing from the domain of the square root function? What? Anything negative. How many negative numbers are there? Infinitely many. So there's a difference. The square root function has a really, really big hole in its domain. Rational functions are only allowed to have isolated gaps in their domain, just single points. Cool. But certainly the square root function is still a function that we can study. It's just not rational. So let's keep on moving along. So we alluded a little bit to these asymptotes. Whenever you have a 0 in the denominator of a rational function, the y values shoot off to plus or minus infinity. Let's just give that a name. We'll call those asymptotes. So an asymptote for a curve is a line. So every asymptote is a line, so that the distance between the line and the curve gets very small as you look further as you look further along the curve. So in order to make sense of that definition, let's just answer the question. Let's find the asymptotes of 1 over x. What lines does it look like 1 over x gets close to? Yeah, but just say it loud. I'm pretty sure you mouthed it, I think. Did you actually say it?
Yeah.
Oh, okay. 0, yeah. At x equals 0, there's 1. And also a y equals 0. Sorry, I encourage people to speak up, but then I just don't listen. That's on me. So it looks like here's an asymptote at x equals 0. And you see that it is an asymptote. As you travel very far along the graph of 1 over x, the graph of 1 over x looks basically like it's the line y equals 0. Well, I wrote down x equals 0, though. Similarly, there's the vertical line x equals 0. If you continue the graph far enough, you see that, yeah, the graph of 1 over x basically just looks like x equals 0 as long as you go far enough along the graph. So it has an asymptote at x equals 0 and an asymptote at y equals 0. I'll be interested in mostly two types of asymptotes. Vertical asymptotes, so those are the asymptotes that are vertical lines, and horizontal asymptotes, which are the asymptotes that are horizontal lines. So what is the vertical asymptote of that function? X equals 0, because that's the one that's a vertical line. And it has a horizontal asymptote at y equals 0. So that's just to make sure that we're understanding some of the notions correctly. And because I want to give an example which will hopefully dissuade people of some preconceptions. Sketch for me a function that has a horizontal asymptote at y equals 2. So here there's a line at y equals 2. It is a perfectly straight line. A vertical asymptote at x equals -2. And a vertical asymptote at x equals 3. Sketch for me a function which gets close to all three of those lines very far away from the origin. And I mean, of course, there are infinitely many things you could possibly draw. Let's see, I think I need a graph of, I need to graph something which is a function, so passes the vertical line test, which gets really close to this line at y equals 2. So let's get really close to that line. I need to get really close to the line at x equals -2. So maybe I'll do that and come back down this way. I need to get really close to the line at x equals 3. And then I need to get really close to the line again, y equals 2. Does anyone feel upset or offended at aspects of this graph? What do you find offensive? Yeah, there's something upsetting about the fact that I crossed that horizontal asymptote. Functions are allowed to cross their horizontal asymptotes. Because horizontal asymptotes only care about what happens very far away from the origin. All of these places where you see crossings, those aren't very far away from the origin. They're fairly close to the origin. All I need is very far away from the origin, the graph of the function and the line are basically the same. And if you go super far in this direction, ignore everything that happens for small x values, is the red graph basically on top of that line? So it's fine. You're allowed to cross horizontal asymptotes. How many people think that? So I certainly haven't crossed any vertical asymptotes. And indeed, you can't cross a vertical asymptote. But the reason for that is pretty small. It's just the vertical line test. Because, well, what if I had exactly this function, but I also added that to it? Now I've crossed that vertical asymptote, but have I violated the vertical line test? Yeah. So you can't cross a vertical asymptote just because of the vertical line test. If you're graphing a curve that is not the graph of a function, you can cross anything. But mostly we're interested in graphs of functions. So there's just some examples of things that can happen. I'll write explicitly. Functions can cross horizontal asymptotes. And notice I said can. They are not obliged to. Certainly the graph of 1 over x never crosses its horizontal asymptote. Cool. So now that we've talked a little bit about asymptotes, let's talk about how you can read them off by just looking at the rational function. So one thing that we've kind of already said is if you have a rational function in reduced form, then whenever the denominator is 0, the y values shoot off to plus or minus infinity. That's all that a vertical asymptote means. Having y values that get really, really, really big without x values that get really, really, really big. That's a vertical asymptote. So a rational function, p of x over q of x, has a vertical asymptote whenever q of x equals 0. So if you want to find vertical asymptotes, just find the zeros of the denominator. That seems reasonable, right? Because that means close to a 0 of the denominator. The denominator is close to 0. When you divide by something that's close to 0, you make the result big. Let's talk about x-intercepts. How do you find x-intercepts of any function? Yeah, it has something to do with 0, but what do you do with that 0? You set y equals 0, the output to be 0. So you would try to solve p of x over q of x equals 0. P of x over q of x equals 0. And I mean, looking at that, it's annoying that there's a fraction on the left-hand side. So how do you get rid of the fraction on the left-hand side? Multiply both sides by q. So you'd wind up with p of x equals 0 multiplied by q of x, which is 0 times anything is. So there's an x-intercept whenever the numerator is 0. So if you want to find x-intercepts at the numerator equal to 0 and solve. If you want to find vertical asymptotes at the denominator equal to 0 and solve. Let's put this in practice. Let's find the x-intercepts and vertical asymptotes of x plus 1 divided by x minus 1. So first let's find x-intercepts. So to find x-intercepts, I should set the numerator equal to 0. There's the numerator, set it equal to 0. What are the solutions to that? Yeah, so there is an x-intercept at negative 1, 0. If you want to find the vertical asymptotes, you need to set the denominator equal to 0. What, Gesundheit, is the solution to that equation? X equals 1. So there is a vertical asymptote at the line x equals 1. Do you think you could do that for the rest of these graphs? Yeah, do it. And maybe I'll even point out that like x-intercepts and vertical asymptotes are things that you can like graph. And if you want to graph a complex function, then you need like 2 dimensions worth of inputs and 2 dimensions worth of outputs. So if you're going to try to graph a complex function, you need 4 dimensions. I don't have that, so I'm not going to try to graph anything complex. There are ways of coming up with graphs of complex functions. What you wind up doing is like having some color coding for what color should represent what complex numbers. Then you wind up with some really compelling and pretty looking pictures. But I won't. Instead, let's do it. So this function, where are its x-intercepts? Plus or minus 1. Where are its vertical asymptotes? There are no real vertical asymptotes. A complex analyst would say there is a vertical asymptote at x equal to y and x equal to negative I. X squared plus 3 divided by x minus 1. Where are its x-intercepts? Does it have any real x-intercepts? Where are its vertical asymptotes? Cool. Does everyone feel pretty okay about that? So let's even think about this a little bit. So I know some things about that function. It should have an x-intercept at negative 1 and a vertical asymptote at 1. But let's try to actually sketch a graph of the thing. And for this particular example, as the following is a way to graph it. I'll say, well, that should basically just look like the graph of 1 over x with some stuff done to it. And the way I'll figure out what stuff to do to it is, well, I'll try to write it in the form you would get after doing polynomial division. So let's see how many times x minus 1 divides into x plus 1. And, right, I'll be using the notation of polynomial long division, but the division will be pretty short. What do I need to multiply the leading coefficient of this by? What do I need to do to multiply what do I need to multiply x by to get x? 1. So the first term in the result of division should be 1. And now, unlike last time, there will be some remainders. It won't divide in evenly. So I'll subtract x minus 1. So that's minus x plus 1, leaving me with a remainder of 2. And let's think about what remainders even mean, how you're supposed to interpret them. So, right, if you ran the division algorithm and you divided 2 into 13, you would get 6 with a remainder of 1. And what does that mean? That means 13 over 2 is 6 plus a remainder of 1, so 1/2. That's all that remainder means. And the same thing is true in polynomial division. The fact that you got 1 with a remainder of 2 means that, well, I'll give myself more space. X plus 1 divided by x minus 1 is 1 with a remainder of 2 over x minus 1. People feel okay? So let's use this to graph. Or maybe before we use it to graph, what do you think I could do to check if that's actually correct? Oh, sure, we could graph them. That's a fine idea. I don't want to, but that's a great idea. You could graph this and you could graph that using a machine and see if they're the same. I don't want to do that because I'm about to graph by hand, so I don't want to spoil what the picture is. Do you think I could just simplify the right-hand side and see if it becomes what it should become? That's certainly an option. So let's do this to check. 1 plus 2 divided by 1 minus x. Oh, x minus 1. So I guess I could get a common denominator. What would that common denominator be? X minus 1. So that's the same thing as x minus 1 over x minus 1 plus 2 divided by x minus 1. Oh, yeah. And let's see, you want to simplify that. Now the denominators are the same, so it's easy to add fractions. So that's x plus 1, nope, x minus 1 plus 2 divided by x minus 1. But what does that numerator simplify to? X plus 1. Does that equal what it has to equal for this to be correct? Yeah. So with this check out of the way, I'm happy. Alternately, right, you could even do that simplification using a machine. You could graph them using a machine. That's a great thing to do. So let's try to graph it now. And maybe to motivate why this is helpful from the point of view of graphing, I'll rewrite it a little bit further. So x plus 1 divided by x minus 1. I now see that as 2 times 1 over x minus 1 plus 1. Gesundheit. After rewriting in that way, is it clear how you can graph that if you start with 1 over x? Yeah, because it's literally 1 over x multiplied by 2, and then there's something being added to x and something being added to the whole function. That's exactly the type of thing that we've graphed by using transformations. I guess you just need to remember which transformation you have to do first. Which one are you supposed to deal with first? Yeah, the stuff away from the function, so that 2 I should deal with first. What happens to a function when you multiply? What happens to the graph of the function when you multiply the function by 2? The y values get bigger by a factor of 2. And then what does adding 1 to a function do to the graph? Shifts everything up by 1. Subtracting 1 from an x moves it right by 1, right? It's the opposite of what you expect. That's everything we need. So I can start with the graph of y equals 1 over x. I'll double all the y values. That looks about like I've doubled all the y values, right? Now I need to shift it up 1 and to the right by 1. So in order to do that, maybe I'll even just keep track of this vertical asymptote and horizontal asymptote and frame them. So that horizontal asymptote at y equals 0, when I shift it up by 1, where does the horizontal asymptote at y equals 0 go? To y equals 1. So there will be a horizontal asymptote at y equals 1. I see a vertical asymptote right now at x equals 0. When I shift it to the right by 1, where will the horizontal asymptote be? x equals 1. So that means my graph should look just like this red graph, but shifted up 1 and right 1. So something like that. That seem okay? Let's just do some quick sanity checks. Where is the vertical asymptote of this function? At 1? But look at the function we started with. Where should its vertical asymptote be? At 1? That's good. So that check passes out. By looking at that, so I guess we didn't keep track of the y-intercept. How do you find the y-intercept of a function? Plug in 0. When you plug in 0 for x, what do you get? -1. Yeah, I believe that y-intercept is around y equals -1. Cool. Where's the horizontal asymptote of this function just by looking at the graph? At y equals 1? Let's see if we can find some general rule that tells us where horizontal asymptotes will be without having to do something difficult like this. So here is maybe the last thing I'll do today. We'll see how time treats me. So if you have a rational function p of x over q of x, then this theorem will tell you where the horizontal asymptote is. And it'll do it one case at a time. And I think let's work out the cases via example in advance. So apparently the three cases are if the degree of the denominator is bigger than the degree of the numerator, if the degree of the denominator is equal to the degree of the numerator, and when the degree of the numerator is bigger than the degree of the denominator. So I'll just write down some example of some function. And let's try to think about what the horizontal asymptote is. And if you recall, the horizontal asymptote should be like what happens when the x values are really big. If it gets close to a single number when the x values are really, really big, then that single number is the horizontal asymptote. So give me like a really big number to plug into this. 60. I'll go to 100 instead, just so I don't have to write down the number 6. Let's think about plugging in x equals 100. So 100 cubed, that'll be like a 6-digit number minus 2 times a 2-digit number. So a 2-digit number divided by a 10-digit number minus a 4-digit number plus 1. If I take a 6-digit number and subtract a 2-digit number, have I actually changed the 6-digit number by much? Basically nothing. If I take a 10-digit number and subtract a 4-digit number, do I have any impact? Yeah. I mean, I guess technically you do. You change it by a little bit, but so small an amount that it's not noticeable. So when you plug in 10 to this 10 squared, 100, you basically just get 10 to the 6 divided by 10 to the 4. Nope, 10 to the 10. That's, I guess, 10 to the negative 4. So that's like 0.0001. Is that close? I mean, so now think about what that's close to. What is that kind of close to? 0. And in fact, if I made this x get even bigger, I would get even closer to 0. So where's the horizontal asymptote of this function? At 0. In general, whenever the degree of the denominator is bigger than the degree of the numerator, there's a horizontal asymptote at y equals 0. What if we flipped this? What if instead it was 10 to the 5th minus 10x squared plus 1 divided by x cubed minus 2x? Could we do a lot of the same logic? We could, right? And then we would wind up concluding that this total is close to 1,000. And in fact, as we plugged in bigger and bigger x values, we would get bigger and bigger y values. So is that y value getting close to a single number as x gets big? No, it's just getting big. So when the degree of p is bigger than the degree of q, then there is no horizontal asymptote. There might be some other type of asymptote, and I won't say anything about what these are, but I'll drop the words oblique or slant asymptotes. And I won't tell you anything about them. However, there will be homework problems about them with the idea that this forces you to read the chapter. Yeah, I mean, all I've done is wrote down two words, oblique and slant asymptote, and then told you that I won't tell you what those mean, unless you come by office hours and ask me to explain them. Then I might. But take a look in the book. So now let's think about what happens when the numerator and denominator have the exact same degree. Let's take not quite that same example. How about 4x to the 4th plus x squared minus 5, 3x to the 4th minus x cubed plus 25x minus 6. And let's play the same game. Imagine you plugged in a really big number for x equal to like 1 billion. If you take that really big number for x squared minus 5, do those make any difference when compared with x to the 4th? No. If you had like a 10-digit number, this would be a 40-digit number. That would be a 20-digit number. It makes no difference. You could do the same thing in the denominator, right? When you plug in a really big number for x, all you really see is 4x to the 4th divided by 3x to the 4th. But what is that equal to? 4/3. You could do that for any polynomial. If you have any, you could do that for any time when the degree of the numerator is the same as the degree of the denominator. You can erase all the low order terms and find out that when the degree of q is equal to the degree of p, there is a horizontal asymptote at the leading coefficient of the numerator divided by the leading coefficient of the denominator. And let's use these rules to just make some conclusions. And maybe I'll add an example right here. X plus 1 divided by x minus 1. What is the degree of the numerator of that rational function? What's the degree of x plus 1? What's the degree of x minus 1? So do the numerator and denominator have the same degree? So that means that, well, in that case, we should look at the leading coefficient of the numerator and divide by the leading coefficient of the denominator. What's the leading coefficient of the numerator? What's the leading coefficient of the denominator? So that should have a horizontal asymptote at. Now look at the graph above. Does that have a horizontal asymptote at 1? Good. Now let's do the rest. So take a look at that function. Where should it have a horizontal asymptote? Nice. This one, x to the 5th minus 1 divided by x to the 5th plus 1. X to the 4th plus x squared plus 1 divided by x to the 5th plus 1. Yeah. Because take a look at it. What's the degree of the numerator? What's the degree of the denominator? Ah. So that puts us in the topmost case. 5 is bigger than 4. So that has a horizontal asymptote at 0. How about this one? X to the 5th minus 1 divided by x cubed plus 1. It has no horizontal asymptote. You can figure out something about what it does asymptotically by thinking about what happens when x is big. You could say, well, that's like kind of close to x to the 5th minus 1 divided by x cubed plus, nope, it's exactly that. You can erase the low order terms. And that basically doesn't change x to the 5th. It basically doesn't change x cubed. And when you erase those terms, you get x to the 5th divided by x cubed. But what is that the same as? X to the 5th over x cubed is x squared. So, this apparently should be when you take a really big value for x, you should get something that's basically a parabola. Let's just check that really quickly. Was that off screen? So that should be a parabola when x is big. And happily, I do have this function graphed by the magic of television. So there's the graph of this function. Do you see a parabola happening in that graph? I mean, not really. The graph isn't big enough. I just graphed it from like -2 to 2. I claim, though, that when you graph it from a big negative big number to a positive big number, you should see something parabolic. Give me a big number. 400, I think, was the loudest number that I heard. Hey, does that look like a parabola? Cool. So I'm done now. If you didn't give me your homework, give me your homework. We'll pick up the same note packet next time, and hopefully get one other new thing. So I don't have to pick everything back.
Like it's fine.
That would be okay.
Yeah. Okay. I'm sorry. Thank you.
Yes.
Yes, I am.
This, and then we'll also be doing
Okay, I was wondering who's taking this.
so there will be another note packet which
Do you know?
how many people are students? Well, if you have access to a printer, that's fine. If you're printed off before class happens, then, I mean, well, I mean, there are typos in the notes anyway, but sometimes they make some corrections in the hours before class. So, if you print it up before class, there might be some corrections that still happen, but nothing major.
Thank you.
Alright, so I have a little dilemma that I just figured out when I got to class. So for this week's homework, I think I did, or for the stuff due this week, I think I did this week's homework because I've been crammed all week. So I just saw it. Is there any way I can get all the homework that's due this week for tomorrow and then have that packet back and return it back in?
Yeah.
So I started with like the 3.1 and it totally didn't occur to me that I was doing
Yeah, remind me of names.
Shackleford, Josh Shackleford. So yeah, I started at the wrong spot. Perfect.
Get it to me.
I can come to the office on Friday.
Try to come
Thursday.
by my office sometime tomorrow.
Okay.
If I'm not in my office, then
What's a good time to get there?
sooner is better.
Okay, sounds good.
So get it to me when you have it done. If I'm not in my office, then you can slide it over.
Okay, perfect. Thank you very much.
Yeah.